Hello there again. It's good to see you. We're going to talk about the stoichiometry of chemistry, and this is a challenging topic, so please take your time understanding this. So, for example, if you were going to make the silk kimono, you'd need 3,000 cocoons. So, chemists look at how much we need. It's just like a manufacturing process. How much do we need to make the product that we want? So, 3,000 cocoons to make one silk kimono. So chemists look at the same thing for chemistry. How much do we need to make the amount of product that we want? So let's talk about that. So we're going to use balanced equations. We talked a little bit about this before, and it's like a recipe. So a recipe calls for certain amounts of things to make a good recipe, and a cookie. It looks like cookies in this case. But we have to have a balanced equation that tells you exactly in quantities how much you need of everything. So for example, if you were going to make a tricycle, you need all these parts to make one tricycle, just like we talked about the bike before. So we're going to use balanced chemical equations, so we have to learn how to balance equations. And we're going to use those to figure out how much reactant is needed or how much product is going to be formed in the reaction. So these are important. And we're going to use this quantitative kind of stuff, and we call that the fancy name stoichiometry. So for example, say this manufacturing can make 640 tricycles in a week. How many wheels are they going to need on Monday morning to get through the week? That's what this question is asking for. It's very similar to what we do in chemistry. So we need 640 tricycles, and there's 3 wheels on every tricycle. So how many are we going to need? We can do stoichiometry with unit analysis. We need 640 of these tricycles. There's 3 wheels on each trike. So if we multiply those together, this number times that number, because they're both on the top of their fractions, we get that many wheels is what we need on Monday to make the 640 tricycles that we want. Same thing we're going to do for chemical reactions. We're going to make sure we have a balanced equation first. We can't do anything until the chemical reaction is balanced, so you have to know how to do that first. And so look at this one. Does it look balanced to you? We've got 2 nitrogens. We've got 2 nitrogens. That's balanced. We've got 3 times 2 is 6 hydrogens, and we've got 2 times 3, 6 hydrogens. Remember, this means gas, and this means yield. So this is the before picture, like the beginning of the week for the tricycle company, all their parts, and this is the ending. Okay, so before and after. We can use this balanced equation to do a lot of different things. So we're going to do that. So for example, we have our 2 nitrogen atoms hooked together. We have 3 of these hydrogen diatomics. Remember, nitrogen likes to be diatomic, hydrogen likes to be diatomic. These are the ones we need to memorize as diatomics. So we've got 6 little hydrogens here, we've got 2 nitrogens here, and then on the other side it's balanced because we see 3 of the blue hydrogens, and then 2 of the darker blue nitrogens. So everything's balanced. 2 nitrogens, 2 nitrogens, 6 hydrogens, 6 hydrogens. So it's all balanced. What can we use? What can we do with all that information? Well, we can say if I have 1 molecule of N2, which I have here, I'm going to need 3 molecules of H2 to make 2 molecules of ammonia. Okay, I can scale it up. Say I want to make a lot. I can take 10 and 30 and make 20. I can also talk about each. I can also do it times. If I know I have an atom here, if I have a 1 in here, that's also meaning 1 mole, which is this number. Remember Avogadro's number. So I actually have 1 times 6.02 times 10 to the 23rd molecules of N2. If I really want to scale it up and do it in mole quantities, I would be 3 times 6.02 times 10 to the 23rd here, and 2 times 6.02 times 10 to the 23rd. So we can talk about this balanced equation in terms of just individual atoms and molecules, or we can talk about it in terms of moles. So there's our moles. And we can also talk about the mass. So if I look at the periodic table and I find nitrogen is 14, I have 2 of them, that's 28 grams. Hydrogen is 1, and I have 2. and I have 3 molecules of that, so that's going to be 3 times 2 grams. So on this side I have 34 grams, 6 plus 28, 34 grams. On here, if I find the molar mass of ammonia, it's 17. I had 2 of them, so that makes 34 grams. Okay, so we can do we have a lot of information once we have the balanced equation. So make sure you know how to balance first. And because these are gases, and if we were at a STP, then we can use that relationship I told you before, that 1 mole is 22.4 liters. So 1 mole nitrogen, that means I have 22.4 liters of that gas. At STP, though, it has to be STP. I have 3 moles of this, so that means I have 60, whatever this is together, 3 times 22.4. And then I have 2 of this, 44.8 liters of ammonia. So I can use a lot of different information because these are in the gas phase. I can even use this STP relationship. So I have a lot going on here. So make sure you understand each one of these lines so you know what's going on. Oh, here, 67.2. So those are the relationships of the gases to each other. So we're always going to make sure that the mass is conserved. If you look here, on this side we have 34 grams. On this side we have to have 34 grams because mass cannot magically appear or disappear. Remember, that's the law of mass. The mass is conserved, if I could talk. So atoms and mass are conserved. They're not magically appearing or disappearing in chemical reaction. Here's another example. We have this gas comes out of volcanoes, and we can take that, add it to oxygen, and turn it into SO2 and water. So that's the balance. See, it's balanced. We got 4 hydrogens, 4 hydrogens. We got 2 sulfurs, 2 sulfurs, 6 oxygens, 4 plus 2 makes 6. So we're good. It's balanced. So what can we look at? Well, we can say that if I look here, there's 2 molecules of this, there's 3 molecules of that, 2 molecules of that, 2 molecules of that, or we could say moles, 2 moles, 3 moles, 2 moles, 2 moles. That's why we have to have it balanced. And they're all gases, so we could do that STP thing that we were talking about. Okay. If we look at the mass on the left side, it has to balance the right side. So always check that to see if you're doing the question right. And here we're figuring out molar masses and figuring out how much grams we have for each side. So this side, we figure there's 164. This side also 164.2. So that always has to be true. You can try that one if you like, and this is at STP, so you can do like we did at the beginning of this set of slides. So let's see if you can do the quiz well. So check this out. I'll give you a second. You can pause me. How many bicycles can you make? Alright, so let's check it out. So we have this many handlebars. That's our limiting. We could make, if we had enough handlebars, we could make that many bicycles. So this is called a limiting reagent or reactant. We only have that many handlebars, so we can only make that many bicycles. Okay, so you're going to have to stop me on this. You're going to have to pause and try this reaction and see if you can figure out the volumes of gases at STP that you're going to produce, which means this side. So try all those for the carbon dioxide and for the water, and then pause me, and then when you have it, have your answers and check yourself, because these are really good kind of quiz and test problems. So you should have got this one if you did it correctly. So I hope you learned a little bit about stoichiometry. It's not an easy subject, so take your time on this and get used to it. And I'll talk to you soon. Have a great day. Bye-bye.